So last time I raised this question that if semiconductor has 10 to the power 12 times smaller conductivity than copper or metallic conductors, why are we so excited about semiconductors? And the answer is that in semiconductors we have an extremely good control on conductivity. For copper or silver or aluminium, whatever conductivity is, it is there. We can't do much about that. But here we can control the conductivity, we can change the conductivity, and we can change it in a desired profile in a particular piece. If we wish that this portion should have this much of conductivity and that portion should have that much of conductivity, we can do that with semiconductors. So that control that we have on conductivity, that is the key factor why this semiconductor electronics is so useful and versatile. So how do we control the conductivity? How do we change the conductivity in a semiconductor? So the first and foremost thing is doping. Very, very important. Doping. So again, taking silicon as an example, pure silicon, as you know, you have that tetrahedral structure and covalent bonding. So silicon and silicon, they are bonded by 2 electrons, 2 sp3 electrons, and each silicon is bonded to 4 other silicons and so on. So you have this kind of structure. Representation, 2-dimensional representation. As I had told, this is a 3-dimensional. I have shown that model, ball stick model. Okay, so don't confuse with double bond, right? 2 lines also is used for double bond, triple bond and so on. These are to represent that it is a covalent bond and 2 electrons are here in this bond. So the structure configuration is, electronic configuration is Z is equal to 14. So you have 1s2, 2s2p6 and then 3s2p2. So these 4 electrons, they go in this sp3 bonding in this structure. Now doping means you purposely introduce some other foreign material in this other than silicon. So silicon is tetravalent, and if we go 1 column right in the periodic table, you have pentavalent elements. Phosphorus is there, arsenic is there. So these are pentavalent in the sense that last this will be s2p3. So 5 outer electrons. Here you have 4 outer electrons. So what happens if I, for example, if I take arsenic and through metallurgical processes we diffuse this little bit of arsenic into this silicon crystal, and the process has to be well formulated and well implemented so that we retain that silicon crystal at the end. We have that same structure of silicon, and some of the silicon atoms are replaced by these arsenic atoms. So that is known as doping. We have doped arsenic into silicon. So suppose a particular silicon is now replaced by arsenic. In this kind of crystal structure, the minimum energy configuration is when 4 electrons go into sp3 quantum states and then they take part in bonding. So that's the minimum energy configuration. So since the crystal structure is still the same, the 4 electrons of these 4 outer electrons of arsenic will again go into the bonding. Okay, so you will have this kind of bonding with this arsenic also. This arsenic is also bonded to the 4 neighbors, in that tetrahedral structure, and 4 of these outer electrons are consumed in that. But the 5th one, the extra electron, cannot go in this bonding, and that is somewhere, let's say somewhere here. It's still bonded to this atom, it's still going around, if you think in that manner about this, but then it's in a much higher energy. If electron is taking part in this bonding, then this energy is very low. Very low means in the valence band, but this one is not bonded here, so it's very weakly bound to this. So as compared to these valence band electrons, this electron will have much higher energy. But then you can also compare, suppose you have a silicon here and you have this bond, and this bond is broken and this electron comes here. This electron is in conduction band. A valence band electron has gone from the valence band to conduction band. This bond is broken and this electron has gone to conduction band. Here the bond is not broken, but there is an extra electron, and that extra electron is outside this bonds. Now this is a new energy level. The energy levels which are created, in which these electrons are there to start with, they are different energy levels which we call impurity energy levels. So in this case, for pentavalent impurities, if this is the valence band and this is the conduction band and this is the gap, this is that gap, the new energy levels are created close to the conduction band, somewhere here. This is the impurity level. Okay, these are new energy levels, and these electrons which are very weakly bonded with this one, these electrons, they lie here. So similarly you have arsenic here and there and there and there, and those electrons are in these impurity levels, and this gap here, this difference here is few tens of milli-electron volts. Maybe 15, 20, 30 milli-electron volts, 40 milli-electron volts of this energy. And remember, kT itself is 26 milli-electron volt. So it's comparable to that. It's just comparable to that. And therefore, through thermal interactions, these can easily go into the conduction band. Through thermal interaction, these can easily go to this conduction band, and then they are free to move anywhere. So that means this electron, which is very weakly bound to this arsenic, so it can go from this atom to that atom and that atom to that atom and so on. It can go anywhere from here to here, and once it goes in this surrounding, the energy is here in the conduction band. So that's the meaning of these electrons going from the impurity level to the conduction band. Okay, and once this electron leaves this arsenic, this becomes a positive ion. Okay, all these silicon which are here, where the bonds are not broken and all bonds are intact, it's electrically neutral. You have same number of protons and same number of electrons. But here the number of protons remains the same and one electron has gone somewhere else. So this leaves behind this positive ions. So this is how we get a doped semiconductor, and this is pentavalent impurities that we have doped, and in this case you have larger number of electrons here. Okay, so to start with, there were some holes and equal number of electrons, but then because of these impurity levels, these electrons have gone here, and so Ne is much greater than NH. How much greater? That depends on how much impurities we have doped, what fraction of total is arsenic. So that will decide this. Normally, let us say ppm type doping. ppm type doping. What is ppm? Parts per million. Okay, parts per million. 1 in 10 to the power 6. So that is called ppm, parts per million. So this type of doping, if you do, then you will have some 1 part in 10 to the power 6. So that's the fraction. You are putting new electrons there, new conduction electrons there. So this Ne will be much larger than this NH. So the charge carriers, remember in semiconductors, if you apply electric field, if you connect it to a battery, then the electrical conduction is because of these electrons, conduction electrons, and also because of these holes, because here also you have some movement of electrons, and so you have I equal to IE plus IH. Now in this kind of doping, this contribution is much more than this, right? This contribution to current because of these electrons, conduction electrons, is much more as compared to the contribution from these holes. So these electrons are negatively charged and these holes are equivalent to positive charge, because once an electron moves to this empty state because of some electric field, if some electron moves this and populates this quantum states, then this quantum state becomes full and this becomes empty. So you can also say that a hole has gone from here to here. So the movement of hole and movement of electron, these valence electrons, they are in opposite directions in an electric field. So holes behave as positive charge. So these holes can be called positive charge carriers, and these electrons can be called negative charge carriers. So the current is dominated by the negative charge carriers, not the positive charge carriers, and therefore this kind of semiconductor is known as N-type semiconductors. Negative type, negative charge carriers are in larger numbers. So N-type semiconductors. Okay, where number of conduction electrons is much larger than number of holes, those are known as N-type semiconductors. Now a very interesting thing happens. What happens to the number of holes? In intrinsic case, we have some number of holes here, some number of electrons here, number is equal. This number of conduction electrons is same as number of holes for intrinsic semiconductors. And now you are putting some impurity, increasing this Ne. This Ne is increased, that is fine. Is there any effect on the number of holes? And yes, there is an effect. profound effect. Why? This number of holes, that density goes down. You remember, you always have a generation of electron hole pair and recombination of electron hole pair. If you have small number of electrons here, an equal number of holes here, there is some probability of electron going and filling a hole. But if you have much larger number of electrons here, you have increased the number of electrons, then the probability that one electron goes and fills this hole and this pair is destroyed, this electron just goes and sits in this quantum state. So you don't have any more electron here, this quantum state becomes empty, and this quantum state which was empty becomes full. So this hole is also gone. So electron hole pair is gone because of this recombination. So the probability that some electron will come here and fill this hole, this probability will increase largely. Right? You have so many electrons or some electron coming and sitting here, this probability will be increased many fold. So through these recombinations, the number of holes will decrease and a new equilibrium will be set up. So Ne increases, so through this doping Ne increases, and at the same time NH decreases. And there is a very simple and interesting relation between this, and that relation is Ne into NH remains constant, independent of doping concentration. If you do not dope and leave it intrinsic, then Ne is equal to NH, and we write it is equal to Ni. So Ne into NH is Ni square. When you dope, Ne has gone up, NH has gone down, but then this relation still holds. This relation still holds for intrinsic or extrinsic. Okay, this is another word, extrinsic. You have intrinsic and extrinsic. When you are doping from external world, you are putting impurities, that becomes extrinsic. So intrinsic or extrinsic, this relation remains the same. Only the temperature can change this Ni. Doping level does not change this. So for example, if you have a silicon, you know there are some 5 into 10 to the power 22 atoms per centimeter cube, and for intrinsic silicon, the number of electrons equal to number of holes is how much? 1.5 into 10 to the power 10 per centimeter cube. We had given this data in one of the lectures. So this is Ni. Suppose you do a ppm doping, 1 ppm doping. That means 1 out of 10 to the power 6 silicon are replaced by arsenic or phosphorus, and each this dopant atom gives you one extra electron in the impurity level and then in conduction level. So this number of electrons, extra electrons that you have put in is 1 per 10 to the power 6, and so that will be 5 into 10 to the power 16 per centimeter cube. So you have put these many extra electrons, and it's such in a large number as compared to this intrinsic one. The total number of electrons per centimeter cube, which you may expect this plus this you are putting from doping, and this was already there. So but 10 power 16 plus 10 to the power 10 will still remain 10 to the power 16. Okay, so you can take this as the conduction electron number density after doping. So what is the number density NH, number density of hole? That will be Ni square divided by Ne, because Ne into NH should remain Ni square, and that is equal to, this is Ni, so that is equal to Ni square 2.25 into 10 to the power 20 and divided by Ne, which is 5 into 10 to the power 16, and of course per centimeter cube, and this is now 0.45 into 10 to the power 4 per centimeter cube, which is just 4,500 per centimeter cube. Okay, so number of holes has gone from 1.5 into 10 to the power 10. From here it has gone to just 4,500. So number of holes has gone terribly down. So that is how you have these charge carrier densities in doped semiconductor, and that is how you are controlling the conductivity, because the doping is under our control. Whether we do 1 ppm doping or what ppm doping, that is under our control, and that will decide what will be the conductivity of this material. The other kind of doping is when you put a trivalent impurity in this silicon crystal. Okay, trivalent is one column left in the periodic table, and you have gallium in that, you have aluminium in that, or boron. So if you have that trivalent impurity, let us say boron, so the outer one will have S2P instead of S2P2. In silicon it is S2P2, in boron or aluminium it will be S2P. So there are 3 outer electrons only. So if this is doped in silicon, what will happen? So suppose you have this silicon crystal, and once again doping is a very sophisticated metallurgical process. You have to retain that silicon crystal structure, the structure that is there. This is this kind of structure in the entire 3 dimensions. So you have to retain that structure and ensure that the impurity is just going and sitting at the site of one silicon ion. So very nice metallurgical processes, or some processes one has to do, and then you have, let us say you have silicon and silicon and so on, that same diagram. And so on. And suppose this particular silicon atom is replaced by this trivalent impurity, let's say boron. What happens? Boron has only 3 outer electrons, sp electrons, s2p. So when it goes into that sp3, there are only 3 electrons that can fill that sp3 energy levels. Okay. So instead of 4, only 3 can be filled and 1 will remain empty. That means in this structure you have one broken bond somewhere. This silicon is providing you 4 electrons, 4 sp3 electrons, but this boron is providing only 3. So one goes here, one goes here, one goes here, and here the bond is not complete. So you have a broken bond, you have an empty quantum state here, and the electron can come here and complete this bond. So you have an empty quantum state, or in other words, you have a hole here. If an electron comes and sits here, this empty quantum state will get populated, or it will be filled. What does that mean? You are creating new energy levels. If a bond is broken here, suppose a bond is broken here and some electron goes and then it sits here, is some energy. But if the bond is broken here and electron comes and sits here, this energy is different from this, slightly different from this energy. These two are different. So these are all same. You have a bond here. So this electron, if electron is here, what is its energy? So that constitutes that valence band. Okay, these energies. So new impurity level energies are created, and those energy levels are created close to the valence band, somewhere here. So this is the impurity level. And these impurity levels are all empty. A broken bond, not broken, it did not exist to start with. Empty, an empty quantum state here exists with boron. Anywhere you have a boron, one of the quantum states will be empty. So you are creating new and empty quantum states, the energy of which will be slightly higher than the top of the valence band. And how much higher? Once again, this is few tens of milli electron volt, right? 10, 20, 30, 40 milli electron volts, that is this. Empty states are there, remember, empty states are there. And since this is only few tens of MeVs and kT is 26 MeV, very easily through thermal interactions, these valence electrons will fill these empty states. There are many quantum states, although the energy is same, and it's not broadened also. It's a quite sharp energy level here. In N-type also there was sharp energy level here. Why sharp? Because in doping, this boron and another boron is widely apart, and therefore boron-boron interaction, impurity levels do not interact within themselves, so it's quite sharp. But nevertheless, all these empty quantum states are very easily they are filled from here, and holes are created in the valence band. So by putting this trivalent impurity in silicon, you are creating many holes, new holes in valence band. And to start with, there were some quantum states filled by electrons in the conduction band, and some holes were there, corresponding holes were there, but now you are putting many more holes through this doping. So in this case what will happen? In this case NH will be much larger than Ne. So in current I equal to IE plus IH, most of the contribution comes from holes. Most of contribution comes from holes because the number of holes is much larger, and this is like positive charge carriers if you talk in terms of holes, and therefore these type of semiconductors are known as p-type semiconductors, positive type, p-type semiconductors. Once again, if the number of holes are much larger here, then electron coming and falling into some hole, that probability will increase. If you have less number of holes, then there is some probability, but if there are too many holes and some electron is there, then it's falling into this hole or that hole or that hole or that hole will be much larger. And therefore through recombinations the number of electrons will reduce from intrinsic. So that same equation will hold, Ne into NH is equal to Ni square. So that holds here also. So both kinds of doping, p-type doping, n-type doping, impurity levels. By the way, there's another name for this. This is known as acceptor energy levels, and the energy levels which were created here when we did n-type doping, they are known as donor impurity levels because they donate electrons here and these accept electrons from here. So this is another name. So these are the kind of doped semiconductor, which is the real strength of all semiconductor electronics. The way you dope, you can create varieties of applications of semiconductors.